All right, one more video on cross products. We're going to see how the cross product is related to the area of a parallelogram and how a triple product, which we'll look at in a second, gives us the volume of a parallelepiped. So let's take a look here at our first example where we're looking for the area of a parallelogram. And the key to this is to pay attention to the order. We have 4 points. And these 4 points are given in 3 dimensions. And we're assuming that they make up a parallelogram. And they do when they're ordered correctly, but we have to be careful. Like, so say I put K here, and then L over here, and then M and N here. What we want to do is check these vectors that are across from each other. So if I check Km and NL, we should get the same vector for this to be a parallelogram. Similarly, M to L and K to N should be the same. So let's go ahead and do that check here. And then I believe I've actually done this incorrectly so that we can see that there is a way of doing this poorly. And we'll try and reshuffle these around so that it works out the way that we want it to be. So M to L. 3 to 1 in the x direction is -2. 8 to 3 in the y direction is -5. 6 to 6 in the z direction is 0. Let's go over k to n. 1 to 3 in the x direction is 2. Already I see that's not the same as -2. It's twisted up our parallelogram by ordering them this way. But let's just keep going. K to n. The y direction 2 to 7 is 5, and then 3 to 3 in the z direction is 0. So we see that's the negative of ML, and that tells us that these are not both pointing in the same direction like our picture is drawn. Let's keep going though. N to L, 3 to 1 in the x direction is -2, and then 7 to 3 in the y direction is -4. And 3 to 6 in the z direction is 3. K to M, we get 1 to 3 in the x direction is 2. 2 to 8 in the y direction is 6. Did I do N? Yeah. K to M. And then 3 to 6 in the z direction is 3. So we see that these are not matching up the way we would imagine if this was actually a parallelogram. So this does make a parallelogram, but this is not the order of the points for it to be a parallelogram. So we're just going to change how we've ordered the names here. So you always need to start by checking that you've got things in the correct order for this. So K, L, M, N, I believe, should do just fine for us. So let's check now. K to N is 2 in the x direction, 5 in the y direction, 0 in the z direction. L to M is 2 in the x direction, 5 in the y direction, 0 in the z direction. There we go. That's what we're expecting. They should be exactly the same. N to M is 0 in the x direction, 1 in the y direction, and -3 in the z direction. K to L is 0 in the x direction, 1 in the y direction, and 3 in the z direction. Okay, so what is happening here? Or is there... Hang on. Oh, N to M, that's a +3 in the z direction. We're good. Okay, I just made a mistake right there. Okay. Okay, so if this is our parallelogram, the area of the parallelogram is going to be equal to the magnitude of 2 non-parallel vectors. So I'll do K to N and K to L. I take those and I find the magnitude of the cross product, that will give us the area of this parallelogram. And I'll do a little proof of that here in a moment. But let's just go ahead and work through it. So this is k to n is 250. Yay, we've got a 0 in there. That'll help with the cross product computation. K to L has another 0. This is going to be a nice simple one. And so we've got the magnitude, and my cross product's going to give me a 15 minus 0 is 15. And then I ignore the middle. I get 6 minus 0 is 6, but we negate the middle term. And then finally I ignore the last components, the 0 and the 3. I'll do 2 times 1 minus 0 is a 2. And then we just need the magnitude of that. That's square root of 15 squared plus 6 squared plus 2 squared. 225 and 36 plus 4 is the square root of 265. That's it. That's our answer. So let's look at why this works. Okay, so the magnitude of a cross product is, do another color here. This is the magnitude of Kn times the magnitude of KL times the sine of the angle between them. So I'm going to take, and I'm going to cut off this triangle here. And I'm going to take that and I'm going to tack it on and see that this rectangle now that I've drawn in red is the same area as the parallelogram, right? It's just kind of moved the parallelogram. I've cut the parallelogram in a way where I'm using the entirety of it. I'm just shuffling that triangle over to the other side to create a rectangle. And this bottom section still has length of k to n, right? I've just taken off this chunk on the left and tacked it on the right. That's the same length there. And the trickier part here is this height, that distance there. And if I look at this angle, this is the angle between Kn and KL. And h with right triangle trig is simply going to be the magnitude of the hypotenuse, which is the length of KL, times the sine of theta. And that really puts it all together. So the area of that rectangle, which is equal to the area of the parallelogram, is the magnitude, well, it's base times height, right? And that base is the magnitude of Kn, and the height is the magnitude of KL times the sine of theta. And that is the magnitude of that cross product. Cool, right? Okay. So that's our, I mean, we're in a, this is nice because, like, if I had a parallelogram on paper, where it was like in two-dimensional, right, where all of our vectors or all of our points just had two components, x and y, then we could do this with some basic trig, pretty straightforward. But these points are given in 3 dimensions, and that makes this problem a lot more difficult. But our cross product allows us to kind of like bypass a lot of that. So let's go ahead and look at parallelepipeds. A parallelepiped is a 3-dimensional parallelogram. So it's going to look where I've got a vector A. Let's start with a vector A here. And a vector B. And imagine that vector B is going into the page, and then a vector C over here. So I've got these 3 vectors, and these are just, this is just one corner of the parallelepiped. And so I'm going to take A and I'm going to copy it over here and copy B here. So this is A again, this is B again, and that creates a parallelogram with those vectors being repeated in that manner. And we can see A is parallel to A, B is parallel to B, And then I'm going to copy C from all 4 of those corners. Here's A, here's, let's try to get these to line up. So this is C again, this is A again. Then I've got C again back here. B is copied there, B is copied. It's a little big. Take C from that corner as well. And then A across the back here. So we see all 4 of the A vectors are all parallel to each other. All 4 of the C vectors are parallel to each other. And all 4 of the B vectors are parallel to each other. And we also see that the front side and the back side are parallel to each other as these parallelograms. And the left and right sides are parallel to each other. The top and bottom are parallel to each other. Okay, so from here, I want to create a formula for the volume of the parallelepiped, which I think it's one of the most fun words to say, parallelepiped. Okay, so this is going to be the area of a base, and we can define the base as any of the 6 sides to this parallelogram. I'm going to go with the bottom side here, times its height. So generally, if I have any shape and I copy that shape all the way up, pretend that the base and the top are exactly the same, and these shapes are, it's just, it can even be at a skew. I just need a height here. Then the volume is always just going to be the area of the base times the height. This is true for any shape. You can take this and just, if you took this and just kind of squeezed it so it was exactly vertical, it would be the exact same volume. You're just taking that volume and skewing it off to one side. So the trick about this is that height that we need to find. So let's kind of look at the base first. Area of the base equals the area of a parallelogram which is going to be the magnitude of A cross B that we just discussed from the previous problem, right? The vectors A and B construct that parallelogram for the base, and so the magnitude of their cross product will be the area of that base. Now, we need to find the height, which is the perpendicular distance between the top and the bottom. This is our height. And if we want to figure out something that's perpendicular to the top and bottom, I want a vector that is perpendicular to both A and B. So we know now that if I take the cross product of A and B, you will get a vector that is in the direction of H, right? So this is parallel to our height. But that doesn't immediately help us find the length. So what we do is we take the vector C and we do a projection of C onto A cross B. And that projection of C onto A cross B has a length that is equal to the height. So that's how we're going to start building up this computation. The area of the base is the magnitude of A cross B. And the height is the magnitude of the projection of C onto A cross B. So let's see, just going to leave the magnitude of A cross B alone for a second. We're going to multiply this. The projection of C onto A cross B is going to be C dotted with A cross B over the magnitude of A cross B. So this, you can take my word for it. If you go back to our dot product problems where we are looking at constructing that projection, you can go back and see that the projection of, say, U onto V, this is U dot V over the magnitude of V squared times V, but this is the same thing as U dot, change this color, sorry. U dot V over the magnitude of V times V over the magnitude of V. So this is a unit vector, and this is the magnitude of the projection. This is a unit vector. So that's where I'm getting this here. One other thing to keep in mind here is that when we're doing that length, we have to be careful. That dot product could actually give us a negative number, so we need to keep an absolute value on that. But we can cross out now the magnitude of A cross B. Right, this, even in the purple that I have over here, I do want to keep in mind that it's really the absolute value of this is the length, because that scalar could be a negative number. So the volume being a positive number, we want to take the absolute value of this. This is called the scalar triple product. And this is equal to A dot B cross C. And you could change the order however you want. So there's a number of different ways that you can switch this around. And those you get by starting with different corners on the parallelepiped. So I could start over and have the base be the left side or the top or something like that. And that's going to give just a different order to A, B, and C in our scalar triple product. So there's a nice symmetry where you can kind of rearrange those and it still gives you the right answer, which is nice because if we actually go to apply this in a formula, just rewrite these in vector form, then I don't have to worry about the order of where I put these vectors in that formula. I don't like looking at the unit vector format for vectors. I like putting them in the angle bracket, just easier for my brain to think about them. So here's A, B, and C, and so the volume of the parallelepiped is going to be the magnitude, and I'll just do it in alphabetical order. A dotted with B cross C. So that is the magnitude of -4, 1, -2, dotted with, in parentheses, B crossed with C. And so we need to do that cross product first here. So let's do B crossed with C over here. This is 1, negative 1, negative 2, crossed with negative 2, 2, 1, which gives us negative 1 plus 4 is 3, 1 plus 4 is 5, but negate it, and then 2 minus 2 is 0. That's nice. Always like a 0. So this will be the magnitude of negative 4, 1, negative 2, dotted with, after we take that cross product, we got a 3, negative 5, 0. So I'll go ahead and take that dot product. I need the magnitude of negative 12 minus 5 plus 0, and that'll be 17 as our final answer. Right, negative 17, but we take the magnitude of it is positive 17. And that's it. That's us applying our cross product to these geometric situations to find areas of parallelograms and volumes of parallelepipeds. So that's it. That's it for the section on cross products. And I will put up some videos on equations of planes here in just a little while. Thank you much, everyone.